Recording in progress.
Sorry for being late. Okay, let's continue 1 second. Is it on? Not on. So we started learning hydrogen atom, and let's continue. Okay, it's just we'll do a lot of math today. So our original triangle equation had this expression, right? Remember, proton, electron need to have a separate kinetic energy, so they have a separate operators. And what you typically learn, right, from the calculus. So xe is a function of x and x. So if you take the derivative, right, you have to do that way, right? You have to take the both capital X and small x into account. And then this coefficient, right? Capital X was this one, and then you can take the partial derivative with respect to xe, right? And then you just get this number, me over m is a constant number, and then you get partial derivative of the center of mass coordinate for given x relative position plus small x was relative position, right? It's this one. And then what is that? If you do take the calculation of this, you just get 1, right? Just get 1. So it just disappears, and then you will get this. Okay. So that's for the first derivative. And then we continue because you have to, in like it's Laplace, and there's a second derivative, right? So second order derivative, to get that, we take the partial derivative again with respect to xe to the row we just derived. So you just repeat the whole process again. Okay, for given xp. And then what we just calculated is this one. So which is me over m square, right? Because for the first term, you'll get it again, right? Get it again. So you have this square term. And then you will have this term. Right. And then you will have a cross term. This is the all algebra. Just do one by one. Okay, so second order derivative. And then you just follow the exact same procedure to get the proton. Proton's kinetic energy operator, right? To calculate that, you need to have this expression, right? That's going to be just everything is the same except for ME becomes MP, right? Everything else is the same here. Okay, so it's all about writing down equation. It's the whole idea is just about the like parameter mapping. And then let's write down the full expression. The full expression of the kinetic energy. So you need to have right m over p square, right? Okay, p square over m. So electron's kinetic energy term will have this operator. And then you have this operator for proton. And then if you just put like what we have just learned into this expression, you just write down the whole thing. Okay, it became rather simple here, right? It became rather simple. And then what we can do is that sorry, one thing I missed in the previous slide. Okay, I'm supposed to have a minus sign here. So that's why these cross terms all cancel out. And you get rather simple result with substitution of reduced mass. This mu is defined as 3 lines, right? Definition. It's called the reduced mass. It's usually used in what is that, the two-body problem, right? You probably have seen it when you study the gravity. But it's quite nice, right? Now you actually separate it into these two nice forms. Okay. And then this thing is coming with a newly introduced an operator with now we will use this one, okay? The center of mass coordinate Laplacian. Okay, so center of mass operator. And then the relative position operator, they're defined as, it's all tedious mess, but it leads to a analytic solution. Okay, that's why we're doing this. Okay, so given this, right, we actually can recast the Hamiltonian into center of mass and then kinetic time for the relative position, and then potential. Okay, so the reason why I have done all this calculation, is the tedious complex calculation, is because of what? Why did we do this? It's because if you go back to the original thing, well, in terms of number of terms, right, you have not really reduced any. Okay, you have not really reduced, but it became like this because, okay, raise hand. Why? Why did we do this? Why do you think we did this? It got better. So actually you'll see the improved result. Why did it get better? Okay.
Potential, we can express potential term by only one parameter.
Yes, correct answer. Okay, 10 points. Good. So, right. So actually because of this is a special case of hydrogen atom, so Coulomb potential is only a function of that distance. Okay, there are relative position is already there as a single parameter. Okay, it's a scalar, right? Quite simple. Coulomb potential is simple, so we want to actually use that as a coordinate. Okay, so to use that small r, we did that conversion. All right, the Coulomb potential is in that shape. Otherwise, actually, maybe why did we do this? Right, probably it doesn't do anything. So it's useful because of potential. Let's try solving this. So we have seen this a lot, so let's try this again. So justification of separation of variables is always what? You guess, okay, you guess the shape of solution and put it in, and then you find it, you can verify, right? It's a solution. So it turns out it does work here. So separation of variable is going to work. So two variables, okay, this one. We are assuming that it is a product of capital R only function and small r only function. And then we'll try to solve the Schrödinger equation. So if you do this if you put this into a Schrödinger equation, you'll get this. You write down the full expression, and then we've done something like this, right? When we were studying converting time-dependent Schrödinger equation to a time-independent one, right? We separated the position variables with from the time variable, but this time we are separating capital R and small r, and then so at that time we did the same thing, right? We have this, and then we divide the entire thing with that function. So after that, you have this. Right. Okay, and then I'll move around the terms. So the second term and the V term will go to the right-hand side. So then I'll do this E plus 1 over, 1 second. You are. Over U are. Okay, let me 1 second. Let me write this way. You can actually group this into like this. Okay, so left-hand side, right-hand side, they are only a function of capital R, only a function of small r. Okay, so what do you get? You're supposed to get a constant, right? Not a function of capital R or small r. So let me call it COM. Okay, the reason you'll find out very soon, the COM stands for center of mass. Okay, so far the logic is what we have experienced previously. Okay, you cast that into a separation of variable form, see if it works. Okay, we'll see if it works. So then if you only look at the capital R, it was this form, SR, okay, center of mass times SR. And this problem, we have solved it, okay? Previously, we have solved it, exact same problem we have solved, which is free particle, free electron. Free electron example, the problem was exactly the same as this, right? So, well, just accept that it's a 3D, all right, 3D. So since it's a 3D, we have to express the answer in terms of 3D. Other than that, it's the same. So you just describe the plane wave. It used to be to the ikx. Instead of ikx in 3D, you use a k vector and r vector. Okay, and center of mass energy is corresponding to this. All right. So overall system, right? Overall system, their center of mass, like the electron proton all together, their center of mass part, the function is like a free particle, right? Free particle solution you get. So it's really a nice, simple result. So now what we're left with is working with the small r. Okay, so we need to work with the small r, which is supposed to be more complex. So let's do that. Okay, so relative position. So this is what is that second part of the previous expression, right? This part. So we're solving this part. And that part, EH, I introduced, which is defined as E minus E center of mass. Okay. So here, right, here is going to become an interesting part. So from here, let me for a while, let me just like forget about like writing down that small r vector. I'll just use the xyz, okay? So we'll forget about the fact that center of mass is moving. Or that is, let's say, center of mass is just fixed, and then solve the rest of this relative coordinate. Okay, so so the Laplacian, what we're gonna do is that the system naturally, right, is like kind of a spherical coordinate is natural thing to assume right here. So we'll use a spherical coordinate system because you can think of the atom is something like a spherical, like electron is like spread around the proton in a symmetrical way. So we'll use this spherical coordinate form of Laplacian. Let me write down the full expression, but you can always find this in any textbook, right? So here what I've done is this the angle part, right? Azimuthal angle and polar angle. These these two theta and phi, they are I put that into the simple form, all right? Laplacian for only those two variables. All right, and then again, all right, here, right, what we're going to do is that the reason I've done it is to separate R and two angles, okay? So there were three variables here, and then here we're going to use an approach that we'll separate R, okay, the radial distance, and then two angles. So what we're doing here is that, again, we'll try separation of variables. Okay, this UR itself was a result of separation of variable, right? Capital R and small r, but we'll separate this again. So we'll intentionally put 1 over r here because it improves the math, okay? Okay, we will use this form and then put that in and see if it works, all right? So this one, if you throw that into an equation, you will get the following equation, which is a bit complicated, but it's just, you are substituting this into a Schrödinger equation above there, all right? So if you put that in, let's see what we're gonna get, which is r square of pi r second derivative plus r squared 2 mu. All of this is in the textbook, and then this textbook, it has all the explanation. I'm just repeating it, but while we work out, I'll just keep explaining things. Okay, so here, right, the theta and phi, the Laplacian, is in fact replaced with the L square. Okay, so I replace that operator with the L square over H bar square, all right? And then if you put that all in together, you will realize that it is in fact this equation with this separation of variable we were trying, right? So you just like remember the logic, okay? So this math is just we follow the calculus rule. But what's important here is that why we are doing this, right? Again, now you will see, actually this is quite nice because this VR, right? So VR was actually, first we thought it's a function of R vector, but in fact, actually it's a function of what? Actually, it's a scalar value only, right? It's just the R. In spherical coordinate system, it's just the R, all right? It's not dependent on theta or phi, the Coulomb potential. So it makes the problem solvable. Okay, so V is function of R, okay? It's not a function of R vector, right? That's Coulomb potential, right? Coulomb potential only depends on distance, and then it doesn't depend on which angle they are at, okay? So their distance is only what matters. And then by introducing spherical coordinate system, you actually have naturally R, small r here. So that's how we arrived at this point. And then this L square, right? L square. Well, actually, it is something you have seen, right? It's what this angular momentum operator was L. I wrote it as L, and that L and this L I introduced for replacing that Laplacian of the angles, right? Are they the same thing? That's the question. The answer is yes. Okay, they are the same expression. We'll just mathematically we can prove it, okay? And then this L, right? Since we have studied previously. Right? When we learned spin, I introduced angular momentum L, right? And then important conclusion was what? They have this special structure of the commutation relationship, right? That is like, Lx, Ly, and then you get Lz as a commutator result, right? And then you can rotate them. So that happens again. And then we will confirm that this is actually indeed that Laplacian, all right? So let's do one by one together. L in 3D, L operator, okay, 3D angular momentum operator is in fact defined as position operator in 3D, outer product, momentum operator in 3D. So it's a bit, looks complicated, but the vector of operators, right, it's a bit complicated, yeah, but they're operator, okay, operator. It does something to a function. So then it's going to give you this, okay? It's vector but an operator at the same time. Each thing multiplied to a vector is what is an operator, okay? So, and then L operator square, we'll use it quite a lot. It is somewhat like this angular momentum operator's inner product, right? So without that hat, right, without that hat, you actually kind of know, that it naturally gives you inner product, right? It's a like length square, but actually it applies to an operator too. So which is giving you the exact same expression like as we usually do, okay? For the regular vector, but except these are actually operators, okay? You apply operator twice. You apply Lx twice, Ly twice, Lz twice, and then add them up. That's L square operator. Okay. So remember this definition, otherwise it's too confusing. And then, okay, so what we need to do is to prove that they are like this is really giving you that the Laplacian theta phi, right? The expression, complex sine theta expression we just saw. So let's do it one by one. It's just a little bit tedious practice of like operator algebra. But whenever you write this, just try to remember, okay, these, what they are, okay? These are all operators. So the momentum operator has a minus IH bar, right? And then it's a partial derivative. So you'll get this minus this, right? Ly operator, Lz operator, we can do exact same thing. Z px minus x pz z x minus x z. Let me quickly just repeat this. X py minus y px operators, which also you can write it as this. Okay, so like we converted to a somewhat, more familiar form of calculus. And then we know that we already have learned this and mathematically proved this, right? Commutation relationship between two components of angular momentum was what? This IH bar, IJK, LK, and epsilon IJK. It's a Levi-Civita symbol. This definition you have discussed previously. Okay. So, right, we wrote out L's definition, okay, all over again. We have learned this. And then next thing, what we haven't done previously is that last time we stopped here, right? When we learned angular momentum operator, we rigorously proved that, okay? We started from angular momentum's definition in classical physics, and then we realized that, well, R and P, right? These like classical terms, we know it's a corresponding operators in the quantum mechanics framework, and then this vector outer product we directly applied to quantum mechanics operators, and then we got L as an operator, and this L operator, right? Its three component X, Y, Z actually is satisfying this commutation relationship, right? Commutation relationship. That's what we learned last time. Now what we want to do is that we just learned this in Cartesian coordinate system. And then now we are working with the coordinate system of a spherical coordinate system, r, theta, phi, spherical coordinate system. So we'll just do this conversion, okay? So this conversion, you already have learned this quite a bit in calculus. So let's just repeat again. You can express x, y, z in terms of r, theta, phi, right? And vice versa. I'll just write it down all over here again. And the reverse way, r is a function of x, y, z, right? So once you know three numbers in any coordinate system, you can actually get other three numbers, right? Using this conversion formula. Okay, we just did a review of calculus. And then, so why did I do this? I just want to write down all of this into spherical coordinate system, okay? So of course, it's going to be too tedious to do everything one by one. So let me just write down the rule, right? How we got there. So any partial derivative, right? Like this can be x, y, or z, whatever it is, right? All x, y, z is a function of r, theta, phi, right? So this partial derivative, you can always do it as the following, right? This rule, right? Okay. So your partial derivative with respect to x, y, or z all can be converted to partial derivative with respect to r theta phi. So this is how you convert the operator between two coordinate systems. Okay, so if you do that, let me just throw an answer right away. Because the calculation is a little bit unnecessary complex, but it's just a kind of a mechanical calculation, right? You just throw in. Now, Lx, Li, Lz, all operators are written in spherical coordinate system. Okay, so Lx, Ly looks a little bit long. Lz appears quite simple. Well, the reason is just the spherical coordinate system is x, y, and z is treated somewhat asymmetric way, right? Z is somewhat special because theta is like defined, right, from z-axis. So for that reason, Lz is appearing as a simple form. So let's start with solving that eigenvalue of Lz operator. Let's solve, see what we're gonna get. Okay, so it's a quantum state that has a distinctive angular momentum of a z component. Okay, that's a eigen, what is that, what we're looking for. So you apply this to a quantum state, some quantum state. One second. This LZ is only a function of like only phi appears, right? You naturally assume that it's okay. It's a function of phi. So eigenvalue equation is this form. So this form, it's very simple to solve, right? Because LZ is just the partial derivative once. So you just solve it. It's an exponential function. Okay. And then M must be an integer. Otherwise, it has an issue, right? Otherwise, it'll have an issue because it's a phi is defined as this, what is it? So azimuthal angle, right? So one after one round, it needs to repeat itself. So that is the same thing as m needs to be an integer. So for that reason, angular momentum around z-axis is quantized. Okay, so angular momentum is what is mh bar. It is quantized. Okay, if you have a z-axis, angular momentum in z component is something like this, right? In xy plane, something is how much it is circling around, right? That's angular momentum, right, around z-axis. That amount needs to be quantized according to this formula. And then the minimum unit is h bar. Okay, so I won't go much deeper in detail for Lx, Ly now. but let's just verify this with given Lx. We calculated, right? Lx in terms of a spherical coordinate, Ly, Lz. Okay. It is possible that we can show that L square operator is indeed this one, the theta pi Laplace, and which let me just write that down. Okay. They're mathematically, you can show that they're equivalent. Okay, so this long derivation, I did it to verify that from this equation, we arrived here, and then meanwhile, right, I replaced this operator with L, and this L is indeed the angular momentum operator, okay? So I did this two-page, two slides derivation to prove that this L is that L, okay, the same L. All right, and then we came back here. Then what we're going to do is that, again, it's a separation of variable problem, right? It's a small r only and theta and phi only, right? There's no mixture of these independent variables. So what do you get? Okay, it is supposed to be a constant again. Okay, so that constant this time, for some reason, let me write it in a very weird form, but well, it's not, it's kind of okay, right? L squared plus L, you can think of as any number can be expressed in that form. So let's do this, okay? So the constant, I actually express in a bizarre form, but later it actually becomes neither. All right. So that's the problem we're going to solve, right? We're going to solve. So first we will solve the theta and phi part first. Okay, theta and phi part first, and then probably next lecture, which I told you that I'll upload it as a video because I cannot make it to the lecture next Thursday, 2 days from now. So and then next week, in the video I'll talk about r, the small r, but let's talk about this theta and phi only today. So to do that, basically we're solving this problem. So we will learn a lot about angular momentum operator today, okay, which is what you used to call orbital back in high school, right? Okay, so electron is circling around the proton, and that circling around will give you angular momentum, right? Like classical thinking and see, and then there will be these distinctive features of a quantum mechanics. So let's inspect these operators. This operator and LZ operator, okay? And then if you do this calculation, I won't do it, but it turns out that it is, in fact, you can swap their orders. Okay, you can swap their orders actually just by looking at their form, okay? From this and that, right? You can actually apply one after the other, and then you can swap their orders. It'll give you the same operation, okay? So they are, in fact, yes, okay. And then this one, right? This is going to the same logic. So It's this. Okay, they are commuting. All right. And then this should work for Lx and Ly as well. We know without actually rigorously calculating Lx and Ly. Why? It's a question. So raise hand, bonus point. Without calculation, we know from the first row, the LZ. Why? Nobody on online, right? No answer on online. Okay. If no answer, let me give an answer. Because it's a symmetry, okay? XY is not really physically special, if you think about it. When we introduce the spherical coordinate system, mathematically Z is special, but we're solving a problem that is like there is no any preference over XY over Z, right? They're equivalent in this problem. Physically, there's nothing really makes them special. It is special because we artificially introduced the spherical coordinate system, but XY are not really, physically, it's not going to be different from Z. Okay, they have equal rights in all aspects. So it's a bit confusing, but it is going to be very bizarre if somehow Lx is not commuting with L square, although, right? Okay, so they are commuting with L square. So L square is a very interesting operator, right? And then let me ask you a quick thing. L itself is commuting with the Lx, Ly, Lz or not? Not L square, L. What about L? It's not, okay. It's not. Yeah, L is not commuting because the L has Lx, Ly, Lz all components, right? And then if you Lx, Ly, Lz, Lx, they're not commuting, right? So if you add them up, it's not commuting. So, okay, for this L square special operator, right? Classically, it's just sort of a angular momentum's magnitude square, right? So it's an operator corresponding to that. Let's find eigenvalues and eigenfunctions of, oh, it's okay, it's an error. 1 second. Let me go to Zoom. Do it again. Good. So we will work on this L square operator. Which was we rigorously proved that it is that Laplacian expression, right? So go back to our equation we were trying to solve here, right? Okay, so we'll solve this, okay? We'll solve this. To do that, it's actually, you realize that it is an eigenvalue problem for this operator, right? You can see that. And then let me summarize again here at this point how we got here, okay? The number of steps we got here is that we first write out time-dependent Schrödinger equation, and then we realize that, well, there are too many coordinates, like electron position, proton position, and then somehow the potential is in the form of relative position magnitude only, right? And then based on that, you can give it a try. Okay, parameter space mapping, right? Xe, xp to capital X and small x. After mapping, what we have done is capital X and small x separation, right? We did capital R actually. Capital R and small r separation, center of mass, and then small r separation, and then it gave us very simple solution for center of mass part, and then we are solving relative position part, this r vector, and this r vector, for the same reason, the Coulomb potential is a special potential. It only depends on the magnitude r, okay, r vector. So it's very nice to work with a spherical coordinate system. So we convert it to spherical coordinate system. And then for that spherical coordinate system, there are three variables. We did a separation of variable into one and the other two, okay? One and the other two. So we're solving the other two, theta and phi here, okay? It has to be a constant. And then this part is becoming an eigenvalue problem. So we'll solve eigenvalue problem here. Okay, it was a very long, complicated story, but mathematically, that's how the logic works. So we're solving this equation. And then let me mark with a little bit of index here, okay? Because that y will depend on index LMN, you'll see very soon. And then in this equation, right, this is an eigenvalue of that operator. This operator, right? So, okay, so let's solve that problem. That problem, what do we do? Again, the same thing, okay? I think it's probably the third time we're doing this again. We'll do separation of variable. Okay, so what we're going to do is that radial, what is that, the angle distribution function, right? Let's assume that it is only a function of theta and only a function of phi, two functions product, okay? We're assuming that the justification is always the same, okay? We give it a try. If it works, it's a solution, right? And then if you throw this in, you will get this form of equation. So it becomes a bit complicated because that Laplacian was actually a complicated one from the spherical coordinate system, right? This differentiation quite complicated. And then it is supposed to be what? Again, constant, right? Two variables equal to each other, right? They're all separated, but the same always. It has to be a constant, right? The constant, let me write it as this, okay? And then this one, right? Actually, we already have solved for LZ, okay? LZ. So this part and this part, actually, we already have solved for, when we solve for LZ, actually the same problem. So we already know an answer. And then that M we just discussed right up here, it is the same thing, okay? So this M is supposed to be an integer. Because of the azimuthal angle phi condition, right? You have to return back to original value, right? Otherwise, the same point will have multiple values. So this part solution is an eigenvalue, eigenfunction, eigenfunction of LZ as well. Okay, so we solved for phi part. Theta part still remains to be solved, but it's complicated. But phi part looks easy, right? So the easy part we already have solved. It's exponential Im phi, right? Okay. Next one, we will solve for theta. Okay, it's a complicated equation, but actually it is known equation. Okay, the solution is known, so you can analytically solve it. It has a name. Associated Legendre equation. Okay. So always the key question is not about how complicated the equation is. It's all about it is solvable or not. It is known to be solvable, then everything is known. It's known to be solvable. So the solution is known. Okay, mathematicians already solved it. And the solution, it's actually his name. His name is just the same, okay. Who solved the problem. Okay, the solution is something like this. In this form, okay. And then the solution itself, right, is forcing L to be integer number. Okay, while you solve this problem, actually, you actually get a condition for L and M. First of all, L needs to be non-negative integer. At the same time, it also gives you N and L's relationship, okay? And M, we know that it's an integer, right? So you also get NLM's L and M's relationship, okay? You need to satisfy that condition to get the solution, okay? It's a result of mathematical structure. And then that PLM is what function? So to be more specific, okay, I replace the cosine theta with an x, okay, to make things simple. It is this known form. Rather complicated, but it is a complete analytic form. Okay, so the bottom line is we know what it is. Okay, we know what it is. So some Mathematica's library must have it, right? MATLAB's library must have it. Python, NumPy, probably it has it as a library, right? So it is known. It is known function. And then let's go back to our original, what is it? The eigenvalue equation. Okay, we were working on this. We are working on this. So L square Y LM theta phi. Okay, let me use the L again, because L, instead of just, what is that? The Laplacian theta phi, if we use L, then it gives us a physical interpretation. It will give you this equation, okay? And then we know its answer, okay? We know its answer. Let me write down the full expression of this y expression. So angular part of the solution of Schrödinger equation, we have solved, analytically solved it. So note that this is also an eigenstate, okay? It is not just an eigenstate of L square, it is an eigenstate of LZ. So LZ you apply to YLM theta phi, right? You can easily see it, right? Because phi only appears at the very end, so on other things just like it's like treated as a constant for phi, and then you get this. So what's our conclusion? So this angular part of the Schrödinger equation solution, right? We solved it, and it is an eigenfunction of a L square operator and LZ operator. So Dirac notation, make things simple. We don't need to bother writing down all the theta phi. We can abstract things away. But nice thing about this solution is that they are actually having labels, right? These solutions are not whatever. There are known analytic functions, and then there are multiple functions, but they can be labeled with the number L and number M. They are both integers with a special condition, right? So that quantum state, that eigenfunctions, we can mark it as a ket LM. And then as I've mentioned, LM has a special condition. So let me draw a table, L and M. L0, and then for that condition of M and L's relative size, M only is limited to 0 in case of L equals 0. L is 1, there are 3 possibilities. L is 2, and so on, right? 3 plus 3. Four minus 4 plus 4, right? And then in chemistry class, we usually learn what these are in terms of orbitals. Okay, there's this name, right? S orbital, p orbital. They are all corresponding to these numbers. LMN has this relationship. And then lastly, okay, we arrive at the final part. So angular momentum in Z, right? Picture. This is a good picture representing what we have solved for. So angular momentum z-axis is all quantized, okay? So here we're giving an example of L equals 2, which is corresponding to d orbital. And then for x and y, we can treat it as this. So I can introduce this orbital, which is L square orbital minus LZ square orbital. And then, one second, LRXY orbital squares. This operator, if you apply this to that quantum state, right? Since we know L square and LZ, we did all the calculations. And then it satisfies the eigenvalue form, right? So this newly defined operator also, right, it shares its eigenfunction. So if you move around this number, right, h bar m square m to L r x y side, what you get is this. And classically speaking, this is corresponding to angular momentum, total angular momentum square, all right? So I separated z and xy planes angular momentum. So let me mark here, for example, this is corresponding to LZ, right? Or talking about L equals 2 case. And then this number is corresponding to LRXY in classical sense, all right? So angular momentum, we separate it into not XYZ actually. In this case, Z is somewhat special because of spherical coordinate system. It is quantized. And then this one, in our XY plane, it has angular momentum square is a given number, and then you put them together, it satisfies this classically expected solution. Okay, sorry, it's a little bit over. Let's finish here today. Oh, by the way, the midterm
Recording stopped.